Hello friends, in this class we will study Taylor's theorem. So first of all, Maclaurin's theorem. Let fx be a function of x, then fx can be expanded in ascending powers of x, that is fx is equal to f0 plus x upon 1 factorial f dash 0 plus x square upon 2 factorial f double dash 0 and so on up to x raised to power n upon n factorial f nth derivative of fx f at 0, it must be 0, and so on. Okay, or we can say if y equal to fx, so in terms of y we can write it like y equal to y0 plus x upon 1 factorial y1 0 plus x square upon 2 factorial y2 0 and nth derivative, then x raised to power n upon n factorial yn 0 and so on, where y not equal to f naught, value of fx at x is equal to 0, y1 0 is f dash, that is first derivative of f with respect to x, and at 0 first order derivative of fx at x equal to 0 and so on. Yn 0 is nth derivative of f at x is equal to 0. So the proof for this is let fx equal to a naught plus a1x plus a2x square plus anx raised to power n plus so on, where a naught, a1, a2 and an are constants. Differentiating with respect to x, this equation number 1 successively, we find f dash x is equal to, so this constant is derivative is 0, and from here I get a1 into 1 plus 2 times a2 into x plus 3 times this and so on. Okay, and similarly double derivative, so differentiate again the first derivative with respect to x, so we get 2 times 2 into 1 into a2 plus 3 into 2 into 1 into a3x and so on. So continuing in the same way, you can see that f and x means nth derivative of fx is equal to n into n minus 1 n minus 2 dot 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 2 and 1, then an plus n plus 1 into n minus 1 n minus 2 3 2 1 an plus 1 x and so on. So putting x is equal to 0 into equations 1 2 3 4 and 5, what we get from there, we can get f0 is equal to a naught, f dash 0 is equal to a1 into 1, that is a1 equal to f dash 0 upon 1 factorial, so f double dash 0 is equal to 2 into 1 into a2, this implies a2 equal to f double dash 0 upon 2 factorial, f triple dash 0 is equal to this, so a3 is this, and similarly for nth derivative at x equal to 0 becomes like this, so this implies an is equal to fn 0 upon n factorial. So substituting these values in equation number 1, we get fx is equal to f naught plus f dash 0 upon 1 factorial, f double dash 0 upon 2 factorial, so on, fn 0 upon n factorial plus and so on. So if y equal to fx, it is just replacing of fx by y, so y equal to y naught plus x into y1 0 upon 1 factorial, x square upon 2 factorial, y2 0 and so on, x raised to power n upon n factorial, yn 0 and so on, and hence the proof of this theorem. There are certain remarks like the function fx would be continuous and differentiable at x equal to 0. And the second thing is Maclaurin theorem. Maclaurin's theorem gives expansion of fx around the point x equal to 0. It should be noted. And now coming to expansion of sine, cosine and exponential series. So what is the benefit of this type of expansion? That we can generate the algebraic form of the sine x, cosine x and exponential of x. Okay, so the expansion of sine series like x minus x cube upon 3 factorial plus x5 upon 5 factorial minus x square. This must be x7 upon 7 factorial and so on. Similarly, cosine 1 minus x square upon 2 factorial plus x4 upon 4 factorial minus x6 upon 6 factorial and so on. And similarly, e raised to power x equal to 1 plus x square upon 2 factorial x power 3 factorial and so on. So expand sin x by Maclaurin's theorem. So how can we achieve those results? Let y equal to sin x, y not equal to sin at 0, that is 0, and find out now the first derivative of this with respect to x, that is cos x, and y1 at 0 means cos 0 is equal to 1. Similarly, y2 is equal to minus sin x, so the value of y2 at 0 is equal to 0. Again, it is minus cos x, so it is minus 1. So plus minus plus minus, like we are getting the values like this. So if we put these values in the expansion and so on, so by Maclaurin's theorem, if we put this in that expansion, that y naught plus x into y1 0 plus x square upon 2 factorial y2 0 plus so on. So if we put their values y naught, y1 0, y2 0, y3 0, okay, and so on, what we get? This value y0 is 0, x1 into y10 is 1. So simply just substituting the values, all these values, but ultimately we get x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial plus so on. Okay, so this is how we can obtain the expansions of the series. Some important points to be noted. Number one, this Maclaurin's theorem or expansion can be used to find approximate value of the function at any point. Number two, to expand any function algebraically and to find integration of functions which cannot be evaluated easily because we can expand these functions algebraically. Okay, and we can use this theorem to find the value of sine 2 radian, putting x equal to 2 in equation number 1. So sine 2 becomes like this, and now you can find out their values, and that will give us the approximate value of sine 2 radian. Now, expansion of functions by Maclaurin's theorem. There are certain questions which you have to do. Expand y equal to log 1 plus e raised to power x by Maclaurin's theorem. Okay, and question number 3 is like this, and question number 4, it is e raised to power sine inverse x, and y equal to log of 1 plus sine x, and question number 5, y equal to e raised to power x. Okay, and now coming to Taylor's theorem. So let f a plus h be a function of variable h. A is any constant value. Then f of a plus h can be expanded in ascending powers of h such that f of a plus h is equal to fa plus h f dash a plus h square upon 2 factorial f double dash a h cube upon 3 factorial f dash a and so on, up to nth derivative term and so on, where f is equal to value of fx at x equal to f dash a is equal to value of f dash x at x is equal to a and so on. Proof of this theorem. So let us consider fa plus h is equal to a naught plus a1h plus a2h square plus a3h cube and so on. So where a naught, a1, a2 and an are constants, differentiating successively with respect to h, the equation number 1, what we get, f dash a plus h is giving me this. Equation number 2, and then double derivative of this is giving me this. The simple derivatives of the respective terms with respect to h, And triple derivative we can have here, this is plus sign, and here it is a n h raised to power n minus 3. Okay, and similarly you can see all these things, and it is h raised to power 0 and n plus 1 into n minus 1 into n minus 2 and so on, 3 to 1 a n plus 1 h plus so on. Okay, and yes, then put h is equal to 0 into equation 1 2 3 4 and 5 that we just obtained previously, and what we get, f a is equal to this, f dash a this, f double dash a is this, and f triple dash a is this, and so on. F and a equal to f and a upon n factorial, where this f and a denotes the value of nth derivative of function f at x is equal to a. Okay, putting in equation 1, we get this one. If we substitute in equation 1, we get this expansion, and hence it is the proof of that Taylor's theorem. Now this expansion is called Taylor's expansion around the point x equal to a of f a plus h. Remarks. Number 1, when a equal to 0 and h equal to x, this gives me fx equal to this thing, x into f dash 0 plus x square upon 2 factorial f double dash 0 and so on. So which is when we do this kind of adjustment, again we are getting the Maclaurin's theorem as a special case of Taylor's theorem. Then the second case is where I replace just h by x minus a in 1. So what do we get? F of a plus h. So h is replaced by x minus a, and it becomes fx. And this is equal to f a plus x minus a f double dash f dash a plus x minus a whole square upon 2 factorial f double dash a plus so on, and all these terms. So this is the expansion of fx in ascending powers of x minus a. So whenever you are asked to find out the Taylor's expansion of any function around x minus a, so you will use this expansion. Okay, and there is a question expand log of a plus h by Taylor's theorem. T means Taylor's theorem. So log of a plus h can be written as it's just like f of a plus h, and it is yeah, just I am expanding this f of a plus h, f of a plus h, f dash a plus h square upon 2 factorial f double dash a. This is just the statement of the theorem. And now here we can, this is because f a plus h is equal to log of a plus h. So this analogy gives me f of h is log of h and f of a is log of a. So f of a is log a, f dash a is 1 upon a, f double dash a is minus 1 upon a square, and so on. These are the terms. And then substituting in the previous expansion, log of x plus h now becomes fa means log a, and then h into 1 upon f dash a is 1 upon a, and then h square upon 2 factorial 1 upon a square plus h cube upon 3 factorial 2 upon a cube, and so on, and so on, plus so on. So therefore we are left with log of a plus h upon a plus h square upon 2a square plus h cube upon 3a cube, and so on. So this is the solution to the problem. Now f of a plus h is if f of a plus h is log of a plus x or log of 2 plus x, so simply put h is equal to x in log of a plus h here for this, and put a equal to 2 and h equal to x in log of a plus h. So then you can expand these functions. Now coming to question number 2, expand tan x in ascending powers of x minus pi by 4. So just like the expansion in terms of x minus a, so where a is pi by 4. So by Taylor's theorem expansion, or simply Taylor's theorem of fx in power of x minus a, just previously in previous two slides we obtained that result. So fx can be written as fx fa plus x minus a f dash a plus x minus a whole square upon 2 factorial f double dash a, and so on. So you should remember that this is the expansion of any function fx around in increasing powers of x minus a. So we will use this expansion now. So fx equal to tan x. Now what is fa? Means f of pi by 4. Then x minus pi by 4, f dash pi by 4, a is pi by 4. Okay. And so on. Then we will find out their values. What is fx, okay, at pi by 4, that is tan pi by 4 1, and f dash x secant square x, so 1 plus tan square, and tan is y, tan x is y, so 1 plus y square, and you can put the value 1 plus f of pi by 4, that's 1 square, and this gives me 1, so 1 plus 1 equal to 2. Okay, and for obtaining this f double dash x, what we will do, we will differentiate this one f dash x once more. So it's just like differentiating this with respect to x. So derivative of 1 is 0, and derivative of y square is 2 times y, and y1 means dy upon dx. And therefore we will just substitute the values 2 times y at pi by 4 and y1 at pi by 4. So we know this earlier. So 2 into y at pi by 4 tan by pi by 4 1, and y1 pi by 4 that we just obtained 2. So it is 4. And similarly we can find out f triple dash x. So again just take this and differentiate it. 2 outside, this is the differentiation of product of two functions, just like this, and if we do it we obtain 6 as the value. And now we have to substitute these values only. So substituting 1 plus x minus pi by 4 into 1 plus second term and so on, all other terms can be put in the previous expansion like this here. Okay, so we get the desired result. So f pi by 4 is 1, okay, plus x minus pi by 4. What is the value of f dash pi by 4? It is, again you can see, it is f dash is 2. Okay, so this is this, and 2 times then the next thing and next thing. Okay, this is the expansion. Now if fxy is differentiable in times in the neighborhood of point AB, and let fa plus h and b plus k be any point in the domain, then there exists a real number theta such that 0 less than theta less than 1, okay, such that f of a plus h comma b plus k is equal to f of ab plus h times this del del x plus k times del del y, f of ab plus 1 upon 2 factorial h into del del x plus k times del del y whole square, f of ab plus so on. So the expansion of this is like this, right? Then where Rn is this 1 upon n factorial h into del x plus k times del y raised to power n, f of a plus theta h and b plus theta k, where theta lying between 0 and 1. So proof of this expansion is, let xy be a point in the domain D such that x is equal to a plus ht and y equal to b plus kt. Okay, so introduce a new function as capital Ft is equal to fxy. Let fxy be equal to ft, and it is written like just f at a plus ht comma b plus kt from here. Okay, so clearly ft is a function of t now. So by Maclaurin's theorem, ft can be written as, okay, f at 0 plus t times f dash 0 plus t square upon 2 factorial f double dash 0 and so on. uh, yeah. Previously, yes. Okay, t cube, and I have expanded it till nth power and so on. So putting t equal to 1 in 1, this equation 1, f1 gives me this. And there, now we find f0, f dash 0, f double dash 0, and fn minus 1, 0. Okay, so f dash t is equal to the dt of f, and because f is a function of x and y also, so its expansion can be obtained by the total derivative. So del del x of f, okay, and then ddt of x plus del del y of f into ddt of y. So f dash t now becomes h times del del x of f plus k times del del y of f, where h is this dx dt of x. I am taking this. Okay, if you just find out ddt of x, that is ddt of a plus ht, if you differentiate we get h, and similarly dt of y gives me k. So just putting their value here, h and k. Okay, so what I am getting dt of f is I'm sorry, h times del del x plus k times del del y of f. When double derivative, just differentiating dt of f once more. So I am getting this one of f. Okay. And if I differentiate it n minus 1 times, then I get h del del x plus k del del y n times n minus 1 times of f, and so on till this, and so on. So putting t equal to 0 into the above results, f dash 0 is this. Okay, because it was a plus th. Okay, t is 0, then it is simply remaining as a, and again b plus kt, and if you put in t equal to 0, I get this. So this is what how I have shown that this is there. Okay, then f double dash 0 is this one, and fn minus 1, 0 is this. And now fn theta is this term. And since ft equal to this, so putting t equal to 0 and t equal to 1, we get f0 is fab and f1 is this. So putting f1, f0, f dash 0, f double dash 0, and so on, all these things in equation 2, we get f of a plus hp plus k equal to f of ab plus this into f of ab plus this square into f of ab, and so on. So this is n minus 1 term and nth term like this, and hence the result. Okay, what are the remarks? In the previous expansion, if we put h is equal to x and k equal to y, then I get this, x plus a and y plus b, and the previous expansion becomes like this, just a replacement of variables, where Rn is this. Yes, again, expansion of fxy in powers of x minus c and y minus b. So simply replace h by x minus c and k by y minus b. So I get f of a plus hb plus k. And if we do it, this and this cancel, this and this cancels, it's only left with f of xy equal to f of ab plus x minus a del del x plus y minus b del del y, f of ab, and this. Okay, so thank you very much.